times cosine omega t, I'll use the whole complex exponential. ei omega t. Now, I have a problem because y here, in this equation, y means the real function which solves that problem. I therefore cannot continue to call this y because I want y to be a real function. I have to change its name. Since this is a complex function on the right-hand side, I'll have to expect a complex solution to the differential equation. I'm going to call that complex solution y tilde. Now, if I call the then that's what I would also use as the designation for the variable. So y tilde is the complex solution, and it's going to have the form y1 plus I times y2. It's going to be the complex solution. And now what I say is, so solve it, find this complex solution. So find the program is to find y tilde. That's the complex solution. And then I say all you have to do is take the real part of that, and that will answer the original problem. Then y1, that's the real part of it, right? It's a function. You know, like this is cosine plus sine. Oh, as it was over here, it'll naturally be something different. It'll be something different. But that part of it, the real part, will solve the original problem. The original real ODE. Now you say, well, I just expect us to believe that. Well, yes, in fact. I think we got a lot to do. So since this is, the argument for this is given in the notes, so read this in the notes. It only takes a line or two of standard work with differentiation, so read in the notes the argument for that, why that's so. It just amounts to separating real and imaginary parts. Okay, so let's now solve this. Since that's our program, all we have to find is the solution. Well, just use integrating factors and just do it. So the integrating factor will be what? E to the, I don't want to use that formula. So the integrating factor will be e to the kt is the integrating factor. If I multiply through both sides by the integrating factor, then the left-hand side will become y e to the kt, the way it always does, prime, y tilde, sorry. And the right-hand side will be, now I'm going to start combining exponentials. It will be k times e to the power I times omega t plus k. I'm going to write that k plus omega t. K plus omega t. I omega t plus k. Thank you. I omega t plus k, or k plus I omega t. KT? Sorry. So it's k times e to the I omega t times e to the kt. So that's k plus I omega times t. Sorry. So y tilde e to the kt is k divided by, now I integrate this, so it's essentially reproduces itself, except you have to put down on the bottom k plus I omega. Now I'll take the final step. What's y tilde equals, see, when you do it this way, then you don't get a messy looking formula that you substitute into in that's scary looking. This is never scary. Now, I'm going to do two things simultaneously. First of all, here, if I multiply, after I get the answer, I'm going to want to multiply it by e to the negative kt, right, to solve for y tilde. If I multiply this by e to the negative kt, then that just gets rid of the k that I put in, and I'm left back with e to the I omega t. So that side is easy. All that's left is e to the I omega t. Now, what's interesting is this thing out here, k plus I omega. I'm going to take a typical step of scaling it. I'm going to scale it. I'm going to divide the top and bottom by k. And what does that produce? 1 divided by 1 plus I times omega over k. What I've done is take these two separate constants and shown that the critical thing is their ratio. Okay, now, what I have to do now is take the real part. Now, there are two ways to do this. There are two ways to do this. Both are instructive. So there are two methods. I have a multiplication. The problem is, of course, that these two things are multiplied together, and one of them is essentially in Cartesian form, and the other is essentially in polar form. You have to make a decision. Either go polar. Sounds like go postal, doesn't it? Or worse, you're like a bear. Savage. Attack it savagely, that's a very good aggressive attitude to have when doing a problem. Or we can go Cartesian. Going polar is a little faster, and I think it's what's done in the notes. The notes don't do both of these. They just do the first. On the other hand, they give you a formula, which is the critical thing that you'll need to go Cartesian. I hope I can do both of them if we if we sort of hurry along. How do I go polar? To go polar, what you want to do is express this thing in polar form. Now, one of the things I didn't emphasize enough probably when I talked to you about complex numbers last time is, so I'll remind you, which salves my conscience and doesn't hurt yours. Suppose you have alpha as a complex number. See, this complex number is a reciprocal. The good number is what's down below. Unfortunately, it's downstairs. You should know, like you know the back of your hand, which nobody knows, 1 over alpha. Since 1 over alpha, so that's of the form, the number I'm interested in, that coefficient, is of the form 1 over alpha. 1 over alpha times alpha is equal to 1. And from that, it follows, first of all, if I take absolute values, that the absolute value of 1 over alpha times the absolute value of this is equal to 1. So this is equal to 1 over the absolute value of alpha. I think you all knew that. I'm a little less certain you knew how to take care of the angles. How about the argument? Well, the argument of 1 over, the angle in other words, the angle of 1 over alpha plus, because when you multiply, angles add, remember that, plus the angle associated with alpha has to be the angle associated with 1. But what's that? 1 is out here. What's the angle of 1? 0. Therefore, the argument, the absolute value of this thing is 1 over the absolute value. That's easy. And you should know that the argument of 1 over alpha is equal to minus the argument of alpha. So when you take reciprocal, the angle turns into its negative. Okay, I'm going to use that now to turn, because my aim is to turn this into polar form. So let's do that someplace, I guess here. So I want the polar form for 1 over 1 plus I times omega over k. Okay, I'll draw a picture. Here is 1. Here is omega over k. Let's call this angle phi. It's a natural thing to call it. It's a right triangle, of course. Okay, now, this is going to be a complex number times e to an angle. Now, what's the angle going to be? Well, this is the complex number, the angle for the complex number. So the argument of the complex number 1 plus I times omega over k is how much? Well, there's the complex number 1 plus I over 1 plus I times omega over k. Its angle is phi. So the argument of this is phi, and therefore the argument of its reciprocal is negative phi. So it's e to the minus I phi. And what's A? A is 1 over the absolute value of that complex number. Well, this is, the absolute value of this complex number is 1 plus omega over k squared. So the A is going to be 1 over that, the square root of 1 plus omega over k, the quantity squared, times e to the minus I phi. You see, I did that. That's the critical step. You must turn that coefficient, if you want to go polar, you must turn that coefficient, write that coefficient in the polar form, and for that you need these basic facts about draw the complex number, draw its angle, and so on and so forth. And now, what's therefore the solution? Once you've done that, the work is over. What's the complex solution? The complex solution is this. I've just found the polar form for this, so I multiply it by e to the I omega t, which means the things add. So it's equal to A, this A, times e to the I omega t minus I times phi. Or in other words, it is, the coefficient is 1 over, this is a real number now, square root of 1 plus omega over k squared. And this is e to the, see if I get it right now. Okay. And finally now, what's the answer to our real problem? Y1, the real answer. I mean the really real answer. What is it? Well, this is a real number, so I simply reproduce that as the coefficient out front. And for the other part, I want the real part of that, but you can write that down instantly. So let's recopy the coefficient. And then I want just the real part of this. Well, this is e to the I times some crazy angle. So the real part is the cosine of that crazy angle. So it's the cosine of omega t minus phi. And if somebody says, yeah, well, okay, I got the omega k, I know what that is. That came from the problem. The driving frequency, driving angular frequency, that was omega. And k, I guess, k was the conductivity, the thing which told you how quickly the heat in that penetrated the walls of the little inner chamber. So that's okay, but what's this phi? Well, if phi, the best way to give phi is just to draw that picture. But if you want a formula for phi, phi will be, well, I guess from the picture, it's the arctangent of omega k divided by k over 1, which I don't have to put in. So it's this number phi in reference to this function. See, if the phi weren't there, this would be cosine omega t, and we all know what that looks like. The phi is called the phase lag, or phase delay, something like that. The phase lag of the function. What does it represent? It represents, let me draw you a picture. Let's try to draw the picture like this. Here's cosine omega t. Now, regular cosine would look sort of like that, but I'll indicate that the frequency, the angular frequency, is not 1 by making my cosine squinchy up a little too much. Everybody can tell that that's the cosine on a limp axis, something for Salvador Dali. Okay. There's cosine, there's cosine of something. So, what was it? Blue? I don't have blue. Yes, I have blue. Okay, so now you'll know what I'm talking about, because this looks just like the screen on your computer when you put in the visual for this. Frequency response order 1. So this is cosine omega t. Now how will cosine omega t minus phi look? Well, it'll be moved over. Let's, for example, suppose phi were pi over 2. Now, where's pi over 2 on the picture? Well, what I do is cosine omega t minus this, I move it over by 1 so that this point becomes that one, and it looks like, the thing will look like this. In other words, I shove it over by, so this is the point where omega t equals pi over 2. It's not the value of t. It's not the value of t. It's the value of omega t. And when I do that, then the blue curve has been shoved over 1/4 of its phase, 1/4 of its total cycle, and that turns it, of course, into the sine curve, which I hope I can draw. So this goes up to there, and then it's got to get back through. See? Let me stop there while I'm ahead. So this is sine omega t, the yellow thing, but that's also, in another life, cosine of omega t minus pi over 2. The main thing is you don't subtract the pi over 2 is not being subtracted from the t. It's being subtracted from the whole expression, and this whole expression represents an angle which tells you where you are in the travel along cosine t. When this quantity gets to be 2 pi, you're back where you started. That's not the distance on the t-axis. It's the angle through which you go through. In other words, this number describes where you are on the cosine cycle. It doesn't tell you, it's not aiming at telling you exactly where you are on the t-axis. The response function looks like the square root of 1 plus omega over k squared times cosine omega t minus phi. And I asked you on the problem set, if k goes up, in other words, if the conductivity rises, if heat can get more rapidly from the outside to the inside, for example, how does that affect the amplitude? This is the amplitude A, and the phase lag. In other words, how does this affect the response? And now you can see, if k goes up, this fraction is becoming smaller. That means the denominator is becoming smaller, and therefore the amplitude is going up. What's happening to the phase lag? Well, the phase lag looks like this. Phi 1 omega over k. If k is going up, then the size of this side is going down, and the angle is going down. Now that part is intuitive. I would have expected everybody to get that. If the heat gets in more quickly, then the amplitude will match more quickly. This will rise and get fairly close to 1, in fact. And there should be very little lag in the way the response follows the input. But how about the other one? Okay, I gave you 2 minutes. The other one you'll figure out yourself.